the task is to find the minimum element in a cyclically sorted rotated array, and we have following information. The array was initially sorted in ascending order, then rotated at an unknown pivot. The goal is to efficiently identify the minimum element. Of course, we can always find a minimum element in any array just by comparing all the elements. But the whole story behind this task is that there are some assumptions that we are making about the data, and those assumptions allow us to create an algorithm which will be a little bit more efficient. And here is an example, of course, as long as the assumptions are met. And an example is as follows. 1, 2, 3, 4, 5, 6, 7, X, very small array. Originally it's sorted, and then something happens. It's getting rotated. So it can be rotated in multiple ways. One example is like this, 4, 5, 6, 7, and then 1, 2, 3. So here is our minimum 1 at this point, and everything else is relatively still sorted here because it was just rotated. And after 1, each number is either greater or equal to the previous number. And here also from the start till this 7 and 1, initially every number is also greater or equal to the previous number, which is an important observation. And if at any point we find that the previous number is greater than the next number, that means that we have our minimum. And the next thing is that we can also have a situation where it was rotated in such a way that it's still originally sorted, but in this case it's like the least efficient case. For us, we would have to go through it all, at least in the linear search case, because we'll do both linear and binary search. And in case of the linear, we would have to go through each element, and then finally we say, okay, there was never this jump between greater and smaller numbers, so the first one is for sure the minimum. And here is our code. We have place to fill 3 solutions: linear approach, linear with a library, so we will use some algorithms from standard library, and binary by hand. We will implement a binary search and adjust it to this case. And then there are some tests which are already prepared for us. We have rotated middle, duplicates, all identical, negative values, no rotation, pivot at the end, single element, and duplicate max on both sides. So all possible cases are covered here. And now let's try to figure out a way in which we can solve it. So of course linear is probably the most if not the easiest, then the easiest, if not the easiest to implement, then the simplest and the easiest to understand, therefore. So we can store the previous element in some variable. Then by the end, if we haven't found the jump, we return the first element, as we said, and here we do iteration for constant auto, and to not make copies, we can take number using ampersand. And now, if the number is smaller than the previous number, then we have found our minimum. Otherwise, we update the previous to the current. And that's it. That's the whole story behind the linear search. Now, using the library is probably the most standard, but could be some kind of efficiency gains generally. But for this particular task, probably your own solution would be faster, but generally it's a good idea to know what kind of standard solutions are available. So we can use std min element, which accepts iterators split from the start till the end. and here nums. And we have to then convert it to a number since it returns a reference or a pointer to that element. But we can, using star operator, convert it back to the number. And that's one approach, which generally is the most advised, but in this case probably will be a little bit slower than the other ones. And here we use 2 pointers or 2 indices, one starting at the very left or at the very start of our array, the other starting by the very end of the array. And we'll try to move either the left or the right by removing completely half of the elements that we consider in each iteration. That's the idea behind the binary search, and you will see in a second how it works. Left and right. Yeah. So while we still have this condition met, then we do something, and once it's no longer true, that means that our result sits here in the left. And so we'll be moving the right mostly, and by the end the minimum will be here. So now, always in the binary search, we first take a look at the middle between the current range. So left and right will be moving all the time, but at the beginning we start with the widest possible range. So we take the very first element and the very last element, and then we try to find the middle between them. And the middle, of course, is left plus right divided by 2. And now we have only 3 cases. So the element, those were all the indices, by the way. And now we compare the elements, so the values that sit under those indices. And we compare it to the right, and by the end it's under the left. So either it's smaller, the one at the middle is smaller than the one on the right side, and sorry, forgot to close. Or there are only 3 cases, or it's greater, or they're equal. And of course, if it's neither smaller or greater, then it's the last case, so we don't have to do anything. And if they're equal, that means what? That for sure, even if our current middle is the minimum, then we will not lose it by moving the right by 1 to the left, decrementing right. Since they're equal, even if we have the case that we already found the minimum, then we can safely move the right to the left, because we still have it at the middle. Then we can move either left to the middle plus 1, or the right to the middle. So we disregard the half of our current elements each time, and those are all the 3 cases, and there is not an option that we have missed anything. That's it. So now let's try to compile. And 42. So I made the same error 2 times. Okay, that was it. And of course, I mixed up the last case. Yeah. If it's greater, then we move the right, and if it's smaller, then we move the left. And all the cases passed. As we rotated middle with duplicates, all identical, negative values, no rotation, pivot at the end, single element, and duplicate max. And the same for all of our implementations. So, couple ways in which we can solve that problem, just to give you some ideas.